Hello and welcome back to the lecture on applied econometrics.
In this lecture, we will cover the concept of power of a test. Now, power of a test is a concept that is very important when it comes to hypothesis testing, and we need to decide whether to accept or reject the null alternative hypothesis. Now, power of a test could be sort of conceived as the probability of making a correct decision, probability of correct decision of a correct decision when given your null is false. Null is false. So it means, let's say we actually impart training to the students of VGSOM or Python training, and the null hypothesis would be that there is no status quo change. So H naught is no impact of training, and H1 is impact of training. There is some positive impact of training. Let's say it's a one-sided test, no impact of training, and H1 is, or HA is there is a positive impact of training. Now, if I think it in terms of the power of a test, I would say probability of correct decision, probability that I could identify the positive impact of training given that there is a positive impact of training, right? So essentially, we also say power is 1 minus type 2 errors. If we go back to the definition of type 2 error, type 2 error would be, type 2 error is, if you recall it correctly, type 2 error is that type 2 we basically deal with the false negatives, right? So essentially, we wrongly identify something as negative when in reality that is positive, right? So for example, we wrongly identified that there is no impact of training, so we have wrongly identified it as negative, whereas there is a true impact, right? So we have basically found that there is no status quo change, whereas there is status quo change, right? So we have given example of like, for example, say we say no COVID, no COVID, or say no diamond, no diamond, where there is really COVID, or say we say that no training impact, where there is really a training impact, right? Or say no theft, or people are not thief, where there is people are really thieves. I mean, yeah, basically no thief. So these are the cases where they are where people are actually, where there is COVID or diamond, or there is training impact, and so forth. In reality, let's say, in reality, let's say. So these are the cases of type 2 error, and I claim that type 2 error, a power of a test is 1 minus type 2 error. So if I try to actually see that, so type 2 error is essentially, type 2 error is essentially, type 2 error is essentially we wrongly identify something as negative when in reality that is positive. So power, we can say type 2 error, 1 minus type 2 error is power. So it is going to be the probability of rejecting the null when in fact the null is false, right? Null is false. Okay, so that's basically the idea of power. Okay, so you are basically correctly identifying the cases when the null is false. Okay, so there are two things: you are correctly identifying, and basically we are identifying those cases where the null is false. So essentially, unlike the type 1 error, when you're talking about type 2 error, And we are basically talking about two different distributions because we are talking about the alternative hypothesis here. So null hypothesis, it has a distribution, and the moment I bring in another hypothesis, which is alternative hypothesis, it means that I'm considering the population, the null and alternative hypothesis population, they are different. So basically the samples drawn from these two distributions, their characteristics are going to be different. So basically when I infer the population characteristics using those samples, we are going to get different population characteristics. So this one, the null hypothesis 1 and on the alternative hypothesis 1, they are actually, in a sense, they are actually drawn from different populations. So to give a better example, like to kind of explain this, so the students who get Python training, so they constitute a different population now, okay, and the students who do not get a Python training, they are here, right? So that's another population. Or the diamond is a different population than stone is this population, whereas diamond is this population. Or the people who are not thieves, this is this population, and people who are thieves, this is this population, right? So they're basically different populations. So the moment you identify these populations, so you have an alternative hypothesis. So we are basically talking about two distributions. So that's what you need to remember. And if, let's say, it has a mean mu0 and mu a, for example, now what I have to understand from here is that is after the training, or after, say, let's say after the training, those who have gone through the training actually constitute a different population or not. So that's what I have to understand. So if the training has no impact, so let's say we just take the training example. If the training does not have any impact, so let's say this training has an impact, but if the training does not have any impact, what will happen is that my yellow distribution and the green distribution, they will sort of coincide, because the population are basically going to remain same. The every characteristics are going to remain same. So let me write down training, say, so I'll write mu0 equal to mu a. What I'll write is that the training has no impact, right? Now what we do when we analyze the power of a test is simply we try to see if the difference between these two distribution is actually significant or not, and that we do with a certain procedure, and I'm going to show you that. So what we will do here is, say we take let's say from the previous one, I will take certain samples from each distribution, okay? Say people who have gone through training, I take this information, these samples, and people who does not have gone through training, I take this, the yellow distribution, and people who have gone through training, let's say this is my green distribution. So I take these observations here, okay? And what I do is, I know that what I have to do, I have to calculate the p-value, okay? And I take these observations between from these two distributions, and I see if the mean of these two distributions, the difference between the two means, if we take, and the corresponding p-value is actually, whatever is greater or lower than 0.05, let's say that's our decision criteria. Okay, so whenever we do calculate this power of a test, we always have to define the alpha. Let's say we'll take alpha equal to 0.05, and we say this is a one-sided test, okay? One-sided test, all right? Now that is one case. So let's say in here we have seen that, let's say in this particular case, I have seen p to be less than 0.05. So we will think that, okay, these two distributions are different. Now that is one observation, right? So you have to take n number of observation to come to this conclusion. So let's say if I just keep on plotting, so let's say this is my case 1, and I'll take case 2, case 3, let's say case 4, and let's say I take up to case 10, and what I find is that in each case I take these observations here. Let me just plot like this randomly, and this is here, and let's say I have these yellow dots here. Let's say this is really far, this is really far, this is really away. Let's say this one is close, and this one is, let's say, again very far. Okay, so if I take the mean of all these samples, so I get this, 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 I get this. These are very close. I get this, I get somewhere this. Okay, and let's say the p-value corresponding to this is less than 0.05. This is less than 0.5, but this one is actually greater than this 0.05. This one is actually less than 0.05. Now, since there are n number of cases, since there are so many cases, I will see this one is actually violating, this p-value is actually violating, but the rest of the p-values are suggesting, oops, sorry, the rest of the p-values are suggesting that, let me not do that, let me actually not do that. So the rest of the p-values are suggesting that these two distributions are different. Now the power of it is, what it does is, it is actually, if I have, say, let's say there are 10 such observations and 8, so let's say out of these 10 observations, 10 observations and 8 suggesting difference, 8 suggesting that the 8 suggesting 2 suggesting distributions are same. 8 suggesting distributions are different, 2 suggesting distributions are same. Now, what statistical power would do is that, so in 8 cases, we are able to reject. So we are able to reject the null hypothesis in 8 cases, okay? And in 2 cases, we are unable to reject the null hypothesis. So it is the power, essentially, we are assuming that these two distributions are different. We are assuming that the two, basically there is an impact of the training. And if that is so, then we are able to identify 8 out of 10 cases correctly, okay? Correctly, we can identify. And the power of test is going to be 0.8 because we are able to identify 8 out of 10 cases. Now, a very important question will come is that, well, how did I know in the first place? How in the first place I know 8 are correct? 8 are correct. Yes, my sort of specification, the way I have my samples are showing that 8 correct out of 10, but how would I know that these 8 are correct whereas these 2 are false? I mean, it might have so happened that these 2 are correct and 8 are false, right? So how would I know that the 8 are correct? So where is the sanctity in this claim? Now, to actually talk about that, it actually comes from the design, how we are actually designing the whole power thing, and how we are actually designing the sample size, and some of the other criteria which we are going to talk about. So those are kind of giving sanctity to the whole thing called power of a test, right? Now, we'll talk about that. So a couple of things about power, but in this lecture, let me just finish here, and I will talk about a couple of characteristics about the power and how actually you can design the power of a test. Thank you.